This is part 2 of 4 of my videos on the kinematics of how a rangefinder does the math and how to evaluate the effect of gravity when shooting up or down at something. So this video will be on 0 degrees, and then after this I'll have one for 60 degrees up and 60 degrees down. Okay, shooting at 60 degrees, this will be your drop from gravity right here. Here's the shooter, there's the target 40 meters away. Actual point of aim will be right there just above it, so I have to exaggerate this for both illustrative and demonstrative purposes, which actually both mean the same thing. It's just fun to say them. Okay, so we aim up 1.755 degrees above our target, which is 1.226 meters above the target. Again, in reality, that's that mark right there. The arrow travels up in a parabolic path, comes back down, hits the target. At 0 degrees, there is no net gain or loss in velocity, because as the arrow goes up, it loses velocity, but then it gains that velocity back as it comes down if we ignore air resistance. So numbers: distance in the x direction, distance to the target 40 meters, there's gravity, velocity of a modern compound bow approximately 80 meters per second, about 260 feet per second. I've seen some really light arrows that'll go faster than that for people that just do target shooting, but typically if somebody's hunting, they're going to have a heavier arrow with more momentum, and it'll be slower. As I previously stated, velocity in the x direction is about 100% up to about 8 degrees, and we're dealing with angles that are less than 2 degrees when shooting horizontal. So distance over times velocity, distance over velocity is time. Instead of setting them up like this, I like to do a conversion equation where things cancel. 40 meters, I always forget my parentheses or multiplication. 80 meters per second means the arrow is in the air for a half a second total. That means it spends a quarter of a second going up and another quarter of a second going down. Kinematic equation, v naught t plus 1/2 at squared. Velocity times time equals your distance. So this is just your previous distance, which we have none. So we just start with this. Use this right here, 0.25 seconds going up in the air. So the distance at the top of the parabola, right there, d sub p, at the parabola apex, 0.30625 meters. I forgot to mention up until now that I'm carrying out these decimal places to a ridiculous amount because I keep using one number. I get one number and I plug that into a formula to get another number, and then I plug that into a formula to get another number, and it goes on and on. So I'm carrying out these decimal places pretty far most of the time. Now that I got my distance to the apex of the parabola right there as it goes up and comes back down, I can use this. My final velocity will be 0, so it's just like we're throwing a ball up in the air. The final velocity will be 0 as at the top of the parabola right there. So v sub y final, and then I solve for v sub y initial. That means I need to have an initial y velocity 2.450 meters per second. Then I use that to get the angle that I aim up. Here's our triangle, velocity at 80 meters per second, shooting up at some angle, velocity in the y direction, velocity in the x. Take the arc sign to get an angle of 1.755 degrees is how high up we aim. Then we use the distance y over x right there with that angle. That means we aim 1.226 meters high, which I showed in my previous video. So that's how far above the target we aim at 0 degrees. 40 meter target, so that divided by 40 meters means we're only aiming up 3% of the distance in the x direction, so a tiny amount. And here's what it looks like on the diagram. So we're aiming up just a tiny amount here, but I exaggerate these distances for the diagram. There's the shooter, there's the target, you aim up 1.755 degrees or 1.226 meters above the target. So that's what it looks like. This takes care of all the information for shooting at horizontal. We have our distances that we aim up, we have our angles. Now the next video will be shooting up at 60 degrees. Things get more complicated there because we have to take gravity into effect. When we're shooting at 0 degrees, the arrow maintains its velocity. It gets slowed down as it goes up, but then it speeds up as it comes down, maintaining an overall same net velocity. But when we're shooting up, the arrow will be slowed. So a little bit more math involved there, and that'll be the next video.